Now, to conclude this section, we try to look at the arc length as a function. That means now we know that the length of a certain curve from A to B is given by this formula, where here f means dy by dx, or it can be dx by dy, depending on the way we subject from the equation of the curve. And these 2 points will also depend on this particular variable that we are considering, right? Anyway, now see this length, if we start from a certain point, and let's say if we end at, let's say if we start from A and if we end at, let's say 10, then that means this, from the starting point A we go up to the point 10, and we should, for that we should suppose that A is a number less than 10. Okay, we'll consider it as 5. Okay, right. So this means starting from 5 we are measuring the length up to the 10th position, right? And these positions should be given with respect to the variable that we are integrating. That's true. Okay, but that's not the point that I want to highlight in this case, right? And how about the same starting point but with a different end point? How about this one? How about this? Right? See, in all these cases what we have is the length from this point up to this one, right? So if we, that means like if we start from a certain fixed point, and if we mention our upper limit as another variable and write down the remaining stuffs as it is, so this formula acts as a function of x, because now here you have squared the function. The reason for calling this a function is, now if we substitute a certain value for x, now definitely x should be greater than or equal to a, right? So if we substitute a certain value for x, let's say if a is equal to 5 as it was in the previous notations, so here if we substitute s, let's say 7, that means it gives the length from 5 to 7. And how about s 11? That means it gives the length from 5 to 11. In other words, we can look at this equation as a function of x, right? So to do that, you should have a variable at the upper limit position, right? So then it will give you that the length from the starting point towards the end point that is mentioned by x. Also, there is another thing. Now all these derivations are defined on a certain curve, right? So our starting point and the end point should also lie within the starting point, like within the domain of this curve. Okay, now if the curve is defined from, let's say 0 to 100, you cannot have a starting point outside this domain of the curve. Okay, so both starting point and the end point. Now here if we visualize the length equation as a function, starting point will anyway be fixed. So this x variable, the endpoint should lie within the range of the given plot, okay, or the given curve, okay. Right, we will move to another example so it will be clear, like this idea of considering a length function will be cleared with an example. So let's consider the following problem, which is find the arc length function for the curve, this one, and we have to take 1, 2 as the starting point. Now see, in this equation it's very difficult to write x as a function of y, okay, because you have ln x here, so you have to take the inverse of ln x, and that will be a huge mess, right? So this is the only convenient way that we can use the length formula, right? So basically still we have to apply the same formula, but instead of a fixed endpoint we will have a variable for the endpoint as well, okay. So now in the way that they have given the equation of the curve, from there itself you can see that y is written as a function of x. Now be careful, here y is written as a function of x, right? And this x and the x I mentioned above are two different cases, right? So the same variable name is written to express totally different ideas. So you should not mix these two variables when you are writing the length function, okay. So as a precaution, what we can do is we can still consider the representation of y as in terms of t, right? So y is represented as t squared minus 1 over 8 ln t. So there won't be any mixing up with the variables, right? So this upper limit variation, the variable for the upper limit can be denoted with x, and for the stuffs that we do inside the integral we can represent that variable as t. All these things are called dummy variables, okay. So no matter what notation that we use, the effect is the same, right? They are like dummies, okay, right. So given that, now it's just a matter of substituting for the length formula, which is this one. Now here we are representing the x as the length as a function. In other words, when you say to represent the length as a function, that means we have a variable at the end point, okay. So and the rest is the same, right? We have t squared dt. Therefore we should differentiate the given function, which is equal to 2x minus 1 over 8 t. It's 2t, not x. So and here also we have f prime t, okay. Therefore our given variable, now here a is the starting point, and since we are considering all, like since we represent y in terms of x, and as the starting point we have 1, 2, that means this is the x coordinate and this is the y coordinate. So as we are running our variable through the x coordinate, or in other words, as we have converted it to t coordinates, we have t comma y coordinates, right? So we should write the first term, not the second one, okay, right? So it becomes x, and here we have plus 2t minus 1 over 8 whole thing squared. So you can simplify what is inside the square root like this. So for this one we use the a plus b squared identity, which is equal to a squared plus 2ab plus b squared. Okay, and by simplifying it further, you can see that everything is reduced down to this one, 2t plus 1 over 8t, because here you will get it as a square, so with the square root everything will get cancels out. So the answer will be t squared plus 1 over 8 ln t, and then we have to substitute the upper and the lower limit, and remember ln 1 is equal to 0. So basically what we have done is we have written down the length function starting from x is equal to 1. Okay, and we have a curve which is given by this formula, that is y is equal to x squared minus 1 over 8 ln x, and starting from x equals 1 we measure the length. So for example, if we say s3, then we just have to, we don't have to do all the calculations from the beginning, right? We just have to plug in this value. So it becomes 3 squared plus 1 over 8 ln 3 minus 1, and this value will be the length from x equals 1 to x equals 3, right? So it will give you the length from here to here, right? And if you plug in a different value, it will give the corresponding length starting at x equals 1. Now there is one final thing that I want to mention regarding this calculation. Remember, I considered the starting point as 1, 2. There is like, the reason for taking 1, 2 is because I wanted to have two different numbers as x coordinate and the y coordinate, because I wanted to highlight the fact that as we are dealing with the x variable, we need to consider the corresponding starting x variable. But the thing is, you cannot choose any random starting points like that, because the starting point must lie on the curve. Okay, so since our curve is y equals x squared minus 1 over 8 ln x, if x is equal to 1, then the starting point, the corresponding y coordinate should be equal to ln1, is because ln1, since ln1 is 0, this should also be 1. Okay, so we cannot have a starting point like this, right? So definitely the starting point, if we start with x equals 1, then the y coordinate should also be equal to 1, right? Now be careful with that detail as well, right? But remember, if you are taking an integral with respect to a certain variable, then you must take the corresponding variable position from the starting point, because when you say the starting point, you will have x coordinate as well as a y coordinate, so we should be smart enough to choose the appropriate one. Okay, so this concludes the sections 8.1.